Okay. Well, we would like to talk about section 11.8. There it goes. And it's all about something called a power series. Okay, and so we're going to spend sort of the rest of our time talking about power series and some interesting things that we can do with them. That's the plan. Now, we went a little quickly over convergence, right? There are a bunch of tests that we didn't get a chance to really explore in detail. And unfortunately, Stuart put it the sections in order on purpose, and we may need some of those tests that we didn't actually look at too carefully. And so from time to time, I might have to say, yeah, and we'll have to go back and check to see if it converges using one of those tests that we didn't really look at. And so we have to do maybe a little bit of hand waving as we move forward. But what I'd like to do is spend the next few days getting our heads wrapped around the big picture so that later, sometime in the future, when you want to prove the gory details, you can go back and look at those. And of course, if that's bothering you, you can spend a little time right now, a little extra time right now, going back and looking at some of those if you want to. But I think it would be best to get the idea on the table. And maybe you'll have to take some of the claims, some of the theorems on faith. But if you move forward, we'll certainly take some time to go back and prove those. Okay, so that's the plan. So a power series, let's write some stuff down. Let's see if I can get organized here so I can write. Okay, all right, a power series. Let's see what one is. A power series is a series of the form sum n equals 0 to infinity, c sub n x to the nth power. Okay, so for convenience sake, we're going to start at n equals 0 this time, and then run all the way out to infinity. And the reason for that is that when we put in the first n, okay, we're going to get c sub 0 and x, right, to the 0 power. Well, anything to the 0 power is going to be 1. And so what we end up with is just a constant, right? C sub 0. Okay, then we put in 1, we get c1 x to the first, c2 x squared, c3 x cubed plus ... goes on and on and on forever. Now we call this a power series. I mean, maybe for semi-obvious reasons, check out the exponent. It's a bunch of powers, right? So as I let n change, the powers are going up. Another thing you could call this is, well, hey, you know what? This kind of looks a lot like a line, right? A flat line, constant, a linear function, a quadratic function, a cubic function. These kind of look like polynomials. The only difference would be that there are infinitely many terms in this polynomial. So you could call it an infinite polynomial if you wanted to. And I think that would also make a lot of sense here. Okay, so that's the definition. That's what one of these things would be. But check it out. Certainly there are going to be different coefficients for different power series. So the easiest set of coefficients would let all the c's be 1s. Okay, so if all the c's are 1s, then you end up with one that looks something like this, right? 1 plus x squared plus x cubed. We've already seen that one. Okay, and then it might be interesting if these coefficients are something other than 1, right? So we're going to explore a few of these. The next thing that you might notice is that this is a function, right? This is a function of x, and the function is going to depend, right? The value of this function is going to depend on which x you've chosen. So if you choose X to be 1, then you got C0 plus C1 plus C2 plus C3, etc. If you choose X to be 0, then you just get C0 and that's it. So one of the questions is, all right, fine. For each choice of X, we would get a different series. And then it begs the question, what's going on with our series? So then we have to fall back to the first half of chapter 11, and we have to say, well, I don't know, might run off to infinity, or it might go to a number. And if it goes to a number, that's more interesting. We say the series converges, and then those have, well, more applications than ones that run off to infinity, let's say. Okay, so this is really kind of crazy, because what you would have to do is test for which values of X does this actually converge. Right? And so you got to test a bunch of series. So instead of just having a problem where you test a given series to see if it converges or diverges, now you have to test it for lots of values of X, or maybe you have to say what range or what interval. Okay, for which X's would this actually be interesting? And by interesting, I mean converge. How are we doing so far? Good?
Doing good.
Okay, then let's do an example. Here's a nice example. It's the easiest one, right? The first example is, what if we let C sub n equal 1 for all n? All right, then what do you have? Then you got 1 plus x plus x squared plus x cubed plus ... Right? And it begs the question, for which values of X does this converge? So this is going to be the first type of question that we're going to say. I give you the C's, I give you the coefficients, and then I say, all right, now you've got a series. And then the question is, for what values of X does it actually converge? So I don't know, try some. What do you think? Try X equals 0. What do you think? Does this sum converge for X equals 0?
Yeah, I think it converges at 1.
Yes, it does. So here's our sum, right? It's equal to this. We could write it in shorthand notation if we want. N equals 1 to infinity of x to the n. Notice if I write it like this, then I miss the first term, right? The constant term. So you're going to have to keep an eye on the index now. It used to always start at 1. But for a lot of these power series, we're going to start at 0 so that we get the 0 polynomial or the constant term. All right, so what do you get? Put in 0. Well, everywhere you see an x, 0 to a power is 0. So this is 1 plus nothing. So the sum equals 1. So converges. In fact, this is kind of cool because it looks like every power series, no matter what the coefficients are, right, would converge at x equals 0. You see that? Because all the terms, all the dots in our power series are going to all be zeros when I plug in 0. Okay, interesting but boring. Try some other ones. How about this one? When x equals 1, what do we get?
It doesn't,
I think it would diverge because you're just adding up a bunch of ones.
Yeah, I'm thinking you're right there. We just add
Yeah.
up 1 plus 1 plus 1 plus 1 plus 1. That doesn't sound very good, right? Diverges. Okay. What if x is 2?
It would diverge even faster, right?
That's worse. 1 plus 2 plus 4 plus 9, right? Plus 16, that's terrible. So I'm thinking big X's are not really so good, yeah?
It should be less than 1.
I'm kind of thinking less than 1. So then we would say, what about when x equals a half. So test something sort of in the middle, maybe. So what do we get on that one? We get 1 plus a half plus a fourth, right? Plus a half cubed, an eighth, plus a 16th, right? Plus dot, dot, dot. What do you think about that one?
I think that that's getting closer and closer to 1, isn't it?
Close.
Or past 1.
So getting closer to 2, I think.
Oh, right, 2.
I'm feeling like this has to converge. Look, if it's bigger than 1 and it diverges, and it's less than 1 and it diverges, and the only place that it ever converged was at x equals 0, this would be boring. So we better find some values for which it converges. And I'm kind of guessing the ones between 0 and 1 are going to work pretty good. Okay, and so I'm saying, what do we do to test this? We first check the simple divergence test. Are the terms going to 0? Yes. Okay, so that means it has a chance. And then we say, well, are they going fast enough? I don't know. Can we write this in a special way? I think we can. This is the sum, right, of 1 times 1/2 to the nth power, where n equals 0 to infinity. Yeah? Or if you want, you can write starts at 1, and we go to the n minus 1 power. Is this looking familiar now? What is it? It's a what?
Geometric series?
Yes, it is. Good news is we only did one section. So the answer is, if you're going to recognize it, it's probably geometric, right? The only other kind we did were the P series, right? The P series, when we had 1 over something to a power, right? All right, like, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared. Remember those? Okay, so this is geometric. And what do we know about geometric ones? We know that the sum is the first term over 1 minus the ratio. So the first term was 1, the ratio is a half. 1 over 1 minus a half is 1 divided by a half. Sounds like 2. Bingo, got it. Feeling okay about this? Should be. In fact, this is not just geometric. This isn't only geometric, right? When x is a half, but it's always geometric. We can rewrite our sum down here, right? As the sum is n equals 1 to infinity of the first term, right? Which is 1 times x to the n minus 1 power. So if you like it in that form, I mean, here it is starting at 0. You can see why that's a convenient notation. Here it is starting at 1, the way we saw it last week. So you go, wow, look at that. It's geometric. And I think we proved, for which values of x does this converge? And you say what?
Anything equal to or less than 0?
Close.
Less than 1.
I'm thinking maybe less than 1.
Less than 1, yeah.
Yeah, and you got to be a little
Between 1 and
careful
0.
about the ones that go less than 0, right? Because then you got negatives. Okay, and we know that there's some fishy stuff going on with the negatives, but I think what we're going to do is say this. The absolute value of x is less than 1, yeah? I think that's what we said. Okay. It's going to converge when x is between -1 and 1. Okay, and so I know there's some details about the negatives, and we didn't get into those. That was section like 11.5 on what to do when it's negative. That's okay, doesn't matter. You can just think of this between 0 and 1, and we can take care of the negatives later if you want to. Okay, beautiful. And not only that, but since it's geometric, we know what it converges to. What does it converge to? First term over 1 minus the ratio, yeah? So the first term is what? 1. Okay. 1 over 1 minus, what's the ratio?
X.
X. Sure it is. It's X. And when the ratio is between -1 and 1, it converges, otherwise it diverges. And so what did we show? This is super cool. This is the first really, really cool thing. It goes on our list of really, really cool things. Okay, so right there next to maybe derivative of sine and cosine. I don't know where it goes. But if you've got a list of cool things, this definitely goes on it. And if you're not putting this, if you don't think this is cool, I don't know, try the flute, right? Because for math types, this is like one of the coolest things in the whole world. And I'm thinking for non-math types, still cool. I think we proved that last week, didn't we? But what we didn't
Yeah, I
do
think
was,
we talked about that already.
yeah, we talked about this already. How did we prove it? We proved that this was a geometric series, and we know that the geometric series converges. Right? And then we showed that it converged by the multiplying by the ratio and subtract the two. That was our trick. Okay, but I'm thinking we could confirm that this is true by dividing. I seem to remember trying to divide last week. Let's divide a little bit better. 1 minus x. All right, so how do you do this division? You say take 1 and divide by 1 minus x. It's a little weird because usually when we divide, the top is bigger than the bottom. It's a higher power than the bottom. And we keep going till we get a proper fraction, and then we just write this. We say it's done, right? So what we want to do now is sort of the equivalent of adding a decimal and adding a bunch of zeros. Okay, but essentially you just divide the same way. How many times does 1 go into 1? And you say once. So 1 times 1 minus x is 1 minus x. And then we subtract, don't we? So you get 1 minus 1, and then 0 minus a minus x. So we get an x right here. So 1, right, times what would have to be x? And you'd say, well, I think it's x. So then you go this times this, right? You put it right there, and then you'd subtract. So x times 1 is x. That's good. Those subtract like we wanted. X times minus x is minus x squared. And then we have to subtract. Notice that when we subtract, you have to subtract the whole thing. So don't forget to distribute the minus. X minus x, 0 minus a minus x squared, x squared. All right, so how many times does 1 go into x squared? And you say?
X squared.
X squared plus x squared. So then we go this times this. X squared minus x cubed. And then we subtract. And we get x cubed. And so how many times does it go in there? X cubed. And then I think we can say it just keeps going.
That's cool.
Yeah, so that's another way we could confirm, just using pre-calculus stuff, just algebra, right? But it's this part that's weird, isn't it? It's we would have to just keep going. I mean, I don't think that that's a big reach, but the answer is this is only equal to this if you keep going. Otherwise, there's a remainder, right? There's a little bit left over. Okay? And so this is a weird idea that you go on and on and on forever, although it's not that weird because you did this way back in 7th grade when you did 1 divided by 3 and got 0.33333333 and said, go on forever. Okay, so what do we got? I'm gonna write it down again because I like it so much. Watch this. 1 over 1 minus x is 1 plus x squared plus x cubed plus dot, dot, dot. Write that down until it's in your head, because that's some important stuff. So while you're working on memorizing that, here's what I want to do next. I want to share with you Desmos again, because Desmos is like the coolest thing in the world. And so what I want to do, I'm going to do this. How do you do this? This? Yeah, there we go. New blank graph, just in case we messed up the variables or something. I'm going to start with a clean one. Okay, so here we go. F of x is 1 over 1 minus x. So there is our perfectly lovely hyperbola, right, that we know and love. It's got an asymptote at x equals 1. It's got a horizontal asymptote at 0. And so our question is, great, we've got this lovely function. What we'd like to do now is check out these polynomials. P of x. P of x, it's over here, it's a little tiny. What is our first one? Our first polynomial, right, was equal to 1. So my polynomial agrees, right, with my 1 over x right there at that point. Basically, it says it converges when x equals 0. In other words, they're the same value. Are we okay with that idea? 1 is 1. Yeah, okay, we got it. All right, so then what? Then we say plus x. Notice that the first degree polynomial, right, the one that has 2 terms, would be the 1 plus the x. So this is like P2, right, the second polynomial. And so look at what's happening though. We're saying that 1 over 1 minus x looks a lot like this. In other words, if this, can you see way off to the side there? If this is equal to this with the dot, 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 then shouldn't this be approximately equal when I just get a few of the terms? And as I add more and more terms, it gets closer and closer and closer. Well, look, right here around 0, close to 0, these have almost the same value. In other words, I'm approximating this hyperbola using this line. Sound familiar? Everything always comes full circle. What kind of a line do you think that is? That's the what line? Oh, you got to go way back now. Starts with the T. Somebody's got to turn on a microphone and tell me.
I don't remember, but I know exactly what you're talking about.
So if I was going to approximate this curve with a line, which line approximates the curve pretty well at this point?
The tangent line?
That is the tangent line.
Oh,
That is the tangent line.
duh.
So do you remember, I would ask you a question like this. I would say, find the equation of the tangent line to the graph y equals 1 over 1 minus x at the point x equals 0. Should we do it? Here, let's do it, because now it seems like maybe you forgot some of that. You can't forget that. That's like all the calculus stuff from like last year. Or, well, I guess last year. This feels like 10 years ago now, but all right, here we go. How do you do it? What do you need to write the equation of the line? A slope and a intercept, right?
Point.
Mhm.
Yep, point and a slope. Okay, I'm gonna turn this off so you can see this a little bigger, and then I'm gonna turn it back on. All right, so how do we get the slope? We take the what?
Derivative.
Take the derivative. So here's our function. So how do I get the derivative? Some people might want to do this first. Right, so what's the derivative? Minus 1 minus x to the minus 2 times the derivative of the stuff inside. True?
Mhm.
Okay, good.
Mhm.
It's on the final. 1 over 1 minus x all squared is what I think we get. And we want the derivative where? We want the slope at x equals 0, don't we? because we were trying to approximate it at x equals 0. Stick in 0. 1 over 1 minus 0 squared. 1. Slope is 1. And how do you get the intercept?
And plug in that point to the original equation.
Plug it in the original. Plug in 0. 1 over 1 minus 0. 1. So what's this? This is the intercept, and this is the slope. So what do you got? You got y equals 1x plus 1. Okay, here we go. We're coming back. There it is. It's got a slope of 1 and an intercept of 1. This is the tangent line to the curve. It's the approximation of the curve at x equals 0. Meaning that if I were to put in values to f, and we were to put in values to p, then I'm kind of thinking that as long as I wasn't right at 1, that's not good, it's undefined. But if I was close to 0, like if I were close to 0, like maybe I'll say 0.1, then these ought to be pretty close to one another, shouldn't they? As long as I stay close to 0, these two things are close together. If I get further away though, look, this peels away from the line, and the line is a bad estimate. But as long as I'm close to 0, these should be pretty close together. In fact, if I'm really close to 0, they're essentially the same number, aren't they? Okay, well, check this out. What did our thing say? This is just the second polynomial. This is not equal to p. It's only equal when I add infinitely many terms. That's what we're claiming. So why don't we add one more term and see what's happening? Check it out. This is so cool. We're saying that this red thing is being approximated by this parabola now. In other words, the line was really close. In fact, it was exactly right on at 0. And then it stayed pretty close to the red curve for a while. But what I'm saying is that this blue curve is a better approximation to the red curve, and it's better for longer. Check it out. Let's go back here. I'm saying these two things are closer for longer. Does that make sense? Okay, so what do you do next? Add some more terms. Okay, x cubed. If a quadratic function fits this thing really good, then I'm claiming a cubic function fits it even better. Are you guys with me?
Yep.
Sort of with me. Okay, good. So when would the blue one fit the red one perfectly? In other words, it wouldn't just be an approximation, it'd be exactly right on. What would you have to do?
Keep adding more and more terms.
Yeah, how many?
Infinitely many.
Infinitely many. Look, the fourth degree one fits even better. It fits even better. Look, you can't even see the difference between the two. Well, I can't type forever here, so I'm going to just change my notation a little bit. And I'm going to say the sum, right? And now I have to get some kind of index. So I like using I, even though I kind of keep messing it up. It's going to start at 0, and it's going to go to n. And what's it going to be? It's going to be x to the n, yes? And now I need a slider for n. And n is going to go from 0 to 100, maybe, by ones. Okay, why is it messed up? You guys know, come on, catch it for the fifth
X to
time.
the n,
Because
and it needs to be x to the I.
X to the I. This is a real trouble because, of course, Stewart uses n for all the formulas in the book. But if you're going to switch it to Desmos, you got to decide. Maybe what you want to do, and I've debated this, maybe you want to leave this n, which means you want to make this n. But then you can't say n to the n. So now you need the upper limit to be something. Stuart gets away with this because he always makes this upper limit infinity, right? But maybe we could do what we did when we did indefinite integrals and make this a t, and now let t go to infinity. I think next year, next time I do Calc 2, if there ever is another time after this, if education ever goes back to normal, right? I think I'm going to use n because I only mess this up every single day. And so I'm going to maybe make this a t from now on. So you can adopt whatever, you should be more flexible than I am. So you should be able to use whatever notation and it should be okay. Okay, but you know, notation is there to make it easier for you to understand. So adopt a notation that makes the most sense to you.
Mm-hmm.
Okay, so what happens now? I say when t equals 1, right? Maybe we'll back up here. What's going on with my thing here? Why isn't it a slider? I don't know. Something's messed up. T equals 0. Oh, I know why. I know why I didn't use t now. Desmos thinks that t's are for a set of parametric equations. So it defaults to, you know how x always defaults as a real number? T always defaults as the index of a parametric equation. So it's already thinking that you're doing something else. So it's going to get confused. It won't make it a slider. Now what? Well, maybe you could say n goes from little n, right, to, you need another letter up here if I can even highlight it. Can't seem to get it to highlight. Maybe you could say go to big N. But then we used big N for the list of numbers from 1 to 100, right? We already used that letter too. So what do you want for your big number here? M for max?
I know I've seen that sometimes in the book before.
Did they use M before?
They would say it goes to M.
Yeah, we could use M, okay? But what you're gonna see sometimes is that this later, you're gonna go from M to N, right? Go from M to N. And since that's the order, M can't be the top because M comes before N. And so they're gonna use M later. So I don't know what number is good for the top here, okay? I'm gonna use, I don't know what I'm gonna use. I'm gonna use M now. So we'll use M. So now I can add a slider for M, and now it works like a regular slider. And now I can say it goes from 0 to 100 by ones. And then it ought to behave properly. Okay, so what do we got going on here now? What we got going on is when it's 0, we get the horizontal line. When it's 1, right? When it's 1, we get the tangent line. When it's 2, we get a parabola that fits even better. Then when it's 3, it's a cubic, and 4, it's a 4th degree, and 5, 6, 7, 8, 9, 10, check it out. Woo! When we get to a 30th degree polynomial, okay, I'm saying it's fitting pretty good. In fact, on this side, it's fitting really tight. You can't even see any air between them. On this side, of course, polynomials go up or down, depending on if it's even or odd. So on this side, it's not fitting real well over here, yeah? But right through this section, it's fitting really well. Look at how well. In fact, it's good to every decimal place. In fact, if I back up here, back to a 10th degree polynomial, it's good to every decimal place. And then eventually, not quite so good, yeah? Are you with me?
Yep.
Okay, good. But I got a little bit of a problem. And now I have to go back to this. You see it? Whoops. Now let's go back to this. Stop sharing. This thing, this right here. Uh-oh. This right here. Because when I'm looking at it in Desmos, I'm not seeing equals. And look at it again. Here it comes, coming back at you. Do those look equal to you? This is doing this. This is the blue thing. This is the red thing. The red thing look completely different than the blue thing. They're not equal.
But didn't we say it was from like, it worked from 0 to 1?
This is only equal when? When it converges. Because otherwise, what would you get? I don't know, put in x equals 5. Then this side is 1 over 1 minus 5. That's negative 1/4. Everybody agree?
Mm-hmm.
But what do I get when I put in 5 on this side?
Huge number.
Huge number. This goes to infinity. Negative 1/4 is not equal to infinity. Okay, so the equals here is a funny equals. They're not equivalent. They're not equals like in the sense of they're always equal. They're only equal when it converges. So let's go back and look at it. Where do you think it converges? Between
0 and 1.
close.
Mm,
In fact, it's looking good over here, isn't it?
to negative 1 and 1.
Between negative 1 and 1. So when we get a really big one, look at, that's a 77th degree one. That means it's agreeing as I get closer to 1. What's happening as I get closer to 1 on this side? It's going where?
To infinity.
Can't get past 1, right? There's an asymptote. Okay, and what's happening when I get closer to negative 1?
Going to negative infinity.
Look, it's looking good, right? It's looking like it agrees all the way to there. And then they go all the way apart from one another, right? So if I go to 78, it's going to go up, huh? And if I go all the way to 100, it's inching closer to minus 1. In fact, these things agree really well all through this whole section. In fact, if I go to infinity, they're equal, but they're only equal where it converges. So between minus 1 and 1. This begs the question, well, this goes back and it sheds some light on why we were so concerned about when does this converge, right? And convergence of series, because we can only say these are equal when this converges, which means we got to be able to figure out when does this converge. Although looking at the picture, right, I think I can say that this hyperbola is the same as this power series, infinite polynomial, for all the values of x for which it converges. And we already know, because it's a geometric series, that that's between minus 1 and 1. So these two things agree, right? They're exactly equal if I leave the dot, 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 between minus 1 and 1. And if I take off the dot, 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 then they're really close, right? They're close. This is an approximation for this. Okay. That turns out to be really, really cool. Let's explore some other ones. Let's see if I've got some other ones. There's a really nice one. I was going to put it up, but I'm kind of, like always, there's not so much time. There's a really cool, maybe I'll just put it up. Here, we'll just put it on the dot cam. It's in the book. We're not going to get time to explore this, but maybe you'd want to take some differential equations somewhere down the road. Who was doing this? Well, Kepler, who was studying planetary motion, was trying to solve a set of equations and turned out to use some series like this. And then Bessel, who actually was studying a drumhead. Okay, so there's a drumhead. That's like literally a drumhead. Okay, with a rubber sheet going over the top of it, you know, and somebody whacked it. And so then they're saying, what's that going to do? So it's going to, right, wobble back and forth. He was kind of concerned about the real details about this. Like, I want to make a drumhead. I want to know where all the points on my drumhead are when I wonk the drumhead. A similar thing would be, what if I throw a rock in a pond? and I want to know what those ripples look like as they're going out from the where the rock went in. Now, who cares? Well, Bezel did, okay, because he was bored in his house. Maybe it was the Spanish flu. I don't know. Okay, when is that? 1784? Nope, not quite. So it might have been something else. Maybe he just liked studying this stuff. I don't know. But nowadays, right, we do a lot of computer-generated modeling. And so if you want to make a drum head, like in a video game, then you're going to have to know where all those points are to be able to draw all those curves. Check it out. Pretty amazing, huh? There's the drum head, there's the model. And so Bezel said, all right, well, there's the function, right? It's called the Bezel function. It's very cool. It's the sum, n equals 0 to infinity, of x's to a power. In other words, it's a power series like the ones that we were looking at. Although it looks a little more complicated than our first simple example. That's the equation that he's going to use to describe the drumhead. And a lot of other physical situations are described by power series as well. So lots of super cool stuff kind of coming down the road. The rest of section 11.8 is going to talk about, it's going to kind of give you one of these, and then it's going to say, where does it converge and where does it diverge? In other words, it's a continuation of the 5 sections that we skipped. And so here's how I'm going to check to see when it converges and diverges. I'm going to do what we normally do. I'm going to just do this. I'm going to say, hey, looks like it works between -1 and 1. And then when we want to prove it, we're going to have to go back and we're going to have to look at those 4 sections that we skipped in a little bit more detail. Does that seem fair? Okay, so before we start proving these things go where we say they go, let's just look at a bunch of them and see what they do. All right, you got this one written down? That's the granddaddy of all series, so you got to know this one. And the cool thing about series is that we're going to build new ones out of old ones. And right now we only have one. So we're going to build a bunch of new ones using this one. Okay, here we go. If I have some paper, let me get another sheet of paper. I don't know what I did with all my paper. Okay. Okay, here we go. Ready? Here comes a new one. Pretty much what I would do is I would write this down every time until I had that really memorized. And I would probably write it down in both forms, as a sum and as expanded. So in sort of summation notation and in expanded form. Of what? X to the nth power. Okay, we good? Ready? Here comes a new one. Check this out. What if I let x be equal to -x? This is a little weird. Maybe we should have used a different letter. But everywhere I see that x, I'm going to put in a -x. Okay, I mean, I could put in a -u if you want, then it would all be in terms of u. But you know math types, we call everything c and everything x, and every function f. So imagine this is a different x. So I'm going to replace this x with a new x called -x. All right, so what do I get? I get 1 over 1 minus a -x. And then I get 1 plus, right? -x plus -x squared plus -x cubed. Okay, plus ... And since people are sometimes confused about what does the ... mean, we're going to write this in a formula, -x to the nth power. If I put the ... remember, you have to guess what I mean. If I give you the formula explicitly, then there's no guessing involved, which is why math types kind of like this no guessing involved kind of way of writing it. Okay, so what do I get over here? 1 over 1 plus x, yes? It's beautiful. And what do I get over here? I get 1 minus x. This is minus 1 squared. So I get plus x squared. And then I get minus x cubed. And then I get plus x to the 4th. And then it keeps going. And if I clean up this side, since I've got minus 1 to the nth and x to the nth, then what I really have is sum n equals 0 to infinity of minus 1 to the n and x to the n. And we sometimes write it out that way. I guess I should have just written it right here. Minus 1 to the n, x to the n. Okay.
Oh, it's like the alternating.
It's like an alternating series now, isn't it? So this equals is only equal when?
When x is less than 1?
That's a very good question.
Or
When, why don't we write it this way? When defined.
yeah.
Okay, because look at this. What if I put in x equals minus 1? And tell me about the left-hand side.
Oh, it's
Right?
yeah.
Bad news, right? Divide by 0, asymptote. So something that's undefined can't be equal to something else. Undefined stuff is undefined. So sometimes the left part doesn't exist. Do we agree?
Mm-hmm.
Only at minus 1. The rest of the time it exists just fine. Sometimes the right-hand side doesn't exist. Give me some value of x for which the right-hand side doesn't exist. When is the right-hand side undefined? In other words, when does the right-hand side diverge? Okay, we're going to have to go back.
When x is greater than 1.
Yeah.
When x is greater than 1. I was just thinking, why don't you plug in 2? 1 minus 2 plus 4 minus 9
Oh yeah, it's gonna keep
plus
getting
25. It's alternating, isn't it? But aren't they getting bigger and bigger and bigger?
Yeah.
So when I add them up, what's happening to the sum? Bigger and bigger and bigger?
Mm-hmm.
So if you can do that a little bit in your head already, then you're off to a great start. Given the amount of time that we've spent on this, if you're still struggling seeing that in your head, that would not be uncommon. Okay, so what we're working on is being able to kind of see this in our head, but that comes from experience and time. So if you're having trouble, what do? Well, you just go actually look at it. If you can't see it in your head yet, then just go look at the thing. All right, so what does the thing look like? We could just put a few terms here. It looks like 1 minus x plus x squared, right? Minus x cubed, right? So what's it doing? Well, this doesn't look anything like our red curve, but I'm claiming it's going to look a lot like this curve. They're looking pretty much the same there on a cubic, aren't they? But only between what and what? Maybe between minus 1 and 1?
Yeah, between minus 1 and 1.
That's
Just
what
like
I'm
the
thinking.
last one.
That's what I'm thinking too, between minus 1 and 1. Sum n equals 0 to m of, what am I
F.
trying to do here? Minus 1. What am I trying to do here? Minus
Oh, yeah.
1. Oh, I can just write, well, I'm going to write minus 1 to the n. I kind of like it simplified this way. And then x to the n. I could have put it minus x to the n, yeah? But now a 46-degree polynomial, look, it's fitting pretty good. Look at how good that fits between -1 and 1.
So it's just like reversed.
It's kind of like reversed. Except now what I'm saying is that this function can be modeled with our infinite polynomial, with our power series.
Mm-hmm.
So this polynomial is equal to this power series. We got some good news here too, because when x is, let's see, the alternating one. Okay, so that looks pretty good all the way down to -1. What would it be at -1? It would be
Undefined.
1, 0, 1, 0, 1, 0. So it'd be undefined. Right? But everything else in the middle there, it's going to work for between -1 and 1. Check it out. Maybe I'll do a little bit more detail. For which values did we say this series converges? We said for x, right, greater than, between -1 and 1, right?
Mm-hmm.
Like this, we said this way. Or if you're in a hurry, you could say the absolute value of x is less than 1. What did we do to get our new series? We replaced our x. This is just a little bit too zoomed in. Tell me if it's too small now. Wait a minute. We replaced our x with a -x. So if you want to know for which values does it work, we replace our x with a -x, all of them. So if I stick a -x in here, we would say for the absolute value of -x less than 1. But what is the absolute value of -x?
It's X.
It's just x. It's the absolute value of x. So notice that it still works from -1 to 1. Just like we could see in Desmos. Okay, so what's the deal? The deal is this. Check out this function now. I'll go back over here again. I've got this function, 1/1 plus x. And what I'm doing is I'm modeling it. Okay, I'm approximating it using this polynomial. Now, it begs the question, why do I want to do that? And the answer is, I probably don't. I mean, why would I approximate a function whose values I already know? Are you with me? I mean, I can just write 1/1 plus x. Why would I write it down as 1 minus x plus x squared minus x cubed? Why would I write it in a more complicated way? And the answer is, for the most part, I might not, other than it's kind of interesting. But let's just keep going, playing this game a little bit more, because I think there's some cool stuff coming. Okay, so what did we do? We took our series, okay, we took our power series, and we replaced x with some new function. And we got a new series. So, hey, why stop there? Why not do some more cool stuff? Like, and now on an aside note, now we've got two series now, which means we could replace this x with other things as well. And the more series that we get, the more we're going to be able to make. So you're writing down cool things. Make sure you write down this one. If that's not memorized yet, well, I'm hoping it's going to be by the end of the hour. Now write down this one, because this one's the second cool one. These are on a page called series. Power series I'm supposed to memorize. Okay, we got two of them so far. Now let's let x be x squared. All right, so what was it before? 1/1 minus x. And what did we get? 1 plus x squared plus x cubed plus ... in summation notation, n equals 0 to infinity of x to the n. For x the absolute value of x less than 1. Woo, okay, ready? Here we go. What if we replace all of our x's with a new x that's squared? I would get 1 over 1 minus x squared. True?
Isn't that like similar to a derivative we have?
That's a good question. I think you're a little further ahead of me though. 1 plus x, 1 plus, I got to put in my x squared now, right? Because that's where the x goes. And then I've got what? X squared squared. And then I've got x squared cubed. And then I've got, going down the road, the sum n equals 0 to infinity of x squared to the n. And when would this work? When the absolute value of x squared is less than 1. So what am I claiming? I'm claiming that 1 minus x squared is equal to 1 plus x squared plus x to the 4th plus x to the 6th plus dot, dot, dot. Okay. And you go, not that exciting, but we should be able to put it on here anyway and take a look at it. 1 over 1 minus x squared. Okay, that's this red thing. I'm saying that's going to be approximated by a polynomial that we just built. I was going to type out a few terms, but to speed things up, let's just skip right to the formula. The 2 to the 2 x squared to the n is x to the 2n, isn't it? Power to power multiply?
Yeah.
So why don't we just write x to the 2n? Woo! That's a 65th polynomial though. And look at how well it fits. So tight you can't even see any red.
-1 to 1 still.
And it works from -1 to 1. Because when is the absolute value of x squared less than 1? And I'll let you do a little work with compound inequalities, but this is only less than 1 when x is less than, or when the absolute value of x is less than 1. I'll let you go ahead and think about that. Okay, that's algebra stuff back from pre-calc, but it's probably back from your pre-calc days that somebody did some hand waving and skipping on. Because solving compound inequalities is, well, I'm doing it in my algebra class right now, in my Math 150, I'm doing them right now. And I'm going to spend 1 day on it. And it's 1 day at home online during COVID. So how well are they going to know how to do these? Right? Yeah. So don't be surprised if there's still some algebra stuff we got to go back and do some review on. But I trust you can handle that. Okay, so this is interesting, but let's see if I can make it more interesting. Okay, oh, how much time do I have? Oh, the time, it's getting away from me again. At first I was doing good on these and now I'm running out of time again. So I'm gonna speed up because there's just so much cool stuff here. All right, what if I now, instead of putting an x squared in there, what if I put a minus x squared in there? Then I would have ended up with 1 over 1 plus x squared, wouldn't I?
Mm-hmm.
And what would that be equal to? That would be equal to 1, right? And then I've got to put in a minus x squared, so I'm going to put it in here. I got to put it in here, minus x squared, sorry. It's hard when you get in a hurry. Okay, and then what do you have? You got plus minus x squared squared, right? And then we got minus x squared cubed, and then we keep going. So when we clean this up, we end up with 1 minus x squared, right? Plus, because the minus is getting squared, x to the 4th, minus x to the 6th, plus x to the 8th, plus dot, dot, dot. And we could, of course, write that in summation notation. Okay, so I can do the plus one. Maybe I can do the plus one. But if I did, this wouldn't be it. This doesn't, this is the 1 over 1 plus x squared. Here's the red curve, but this blue thing doesn't model it very well. I need an alternating part, don't I? It's got to alternate. So I need a -1 to the n, to the
Wait,
n.
is it minus x to the 6 or plus x to the 6?
I don't know, did I mess it up? This is minus, this is plus. This is the -1 is cubed, right? So
Yeah.
-1 cubed is minus, and then x to the 6th. So I think it alternates.
Oh, I was looking at the wrong function. Sorry. It was too far up.
Okay. I'm just going to go to 10 because it gets so far away at 100. Check it out. There's the tangent line at 0. But look at this. A parabola fits better. Make it a little bigger for you. But if a parabola fits good, what about a cubic? A cubic wouldn't fit on this red thing at all, would it? So skip the cubic and go to the 4th degree. A 4th degree polynomial fits pretty good, doesn't it? What about a 6th degree polynomial? Fits even better. What about an 8th? Better. What if I keep going? Better, 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 better. Yeah? What if I go, I said I was going to go to 10, but now I want to go to 100. What if I keep going to 100? Better, 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 better. But for which values does it seem to be fitting? Only between
-1 to 1.
-1 and 1. Okay. I'm going to have to call it good sometime. Let me see where I am. I'm going to see if you can do all the homework from 11.8. I think you can. There's going to be some, you're going to have to just try to do the best you can on this homework. Where am I? Oh, I wasn't sharing that. Oh, no wonder. I'm sorry. Here. This is there. Now you should be able to see it. Yeah? Fitting better, 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 better.
That's cool.
From -1 to 1. Okay, I'm going to stop sharing that. Go back to my paper. See if I can recap. This section is going to be a little bit hard to do the homework on. So you're going to do the best you can, and then we're going to figure out what's happening, because there's going to be a lot of questions about power series, and they're going to ask you, for which values does it converge and diverge? So you don't have to go back and use all the tests from section 3, 4, 5, 6, 7, because we didn't explore them in enough detail that you're comfortable with those yet. So what I would do is explore the homework problems and try to do them using Desmos. You don't have to prove them. Just look on Desmos and see if you can figure out for which values it's working. Okay, and if there are some that get a little bit too detailed and they say, hey, use the ratio test. Well, we didn't learn the ratio test. So you got a couple of things you can do. One is you can go back and look at the ratio test and see what it's telling you, or you can just skip it, okay? Because we can only do so much. Katie.
If you understand the ratio test, can you, and like the other tests that we haven't learned, can we use them on our test?
Yes. Anything that you go back and learn, okay, that you spend a little extra time on, you are welcome to use. Okay, so if that makes it a little easier for you to kind of get your head wrapped around it, that's good too. If you want to just look on Desmos and say, well, it looks like it, that's good enough for me as well. Okay, all right, so how does this game go? I'm gonna call it quits on this game, and we're gonna continue this game on Wednesday. But the game is played just like this. You start with a series that you know. And now we know 4 series, right? Because we've built 4 of them now. And then you replace the X, okay, with some other stuff. And when you do, you get a new series. And so we're going to be in the business of building a bunch of series now. And so you can go off and practice and just get kind of familiar with how this is working and the notation and what's going on. And when we come back on Wednesday, what we want to do is build a few more. Okay, and then I think we're going to build some really cool ones. It's going to turn out. All right, so we're on the way down the road here. I think that that's most of section 11.8. do the best you can on the homework, but don't get frustrated if it asks you things from before and you're feeling like you didn't have enough experience yet. You can just skip those ones. Okay, is that enough for today?
So Wednesday, we're going to continue section 11.8.
Yes, we're going to be, well, we're basically easing into 11.9 already. And
Okay.
so we're going to kind of be working on 11.9 on Wednesday.
Awesome.
Okay, questions from you guys just listening in? Carlos, Shane?
No, I was looking at this and seeing that using this power series, we just
Uh-huh.
1/1 plus x squared. Couldn't we use that to prove that the sum, whenever, you know, how we would get like the when we were trying to do the Riemann sums, it would involve inverse trig, and we could never do it.
Uh-huh.
Just to prove that.
Uh-huh. I think we got some cool stuff coming real soon. Because if 1/1 plus x squared is looking like an inverse tangent, then I think you might be anticipating where we're going. Because I seem to remember some of those were really ugly, right? We ended up having trig. And in fact, maybe even this one was looking a little bit familiar. Because if we did something similar, 1/x is really closely related to the natural log, isn't it? And so I think there's going to be something going on here with integrals and derivatives here real soon, like maybe Wednesday. But I'm going to let you think about that a little bit between now and then we'll see what happens.
It always comes back to derivatives.
In this class, it definitely does. Yes, it does. Okay, you guys have a good couple of days, and we'll see you on Wednesday.
Bye.
All right, see you then.
See you.